Okay, hi folks, welcome back. We're back with another National 5 Physics past paper, and as requested is the 2024 written paper, and we're going to do this in 3 parts. So this is part 1, it's questions 1 to 6, that's all the dynamics and space questions, and as usual we're going to the Calder Glen High School National 5 Physics page, and we're looking for National 5 SQA past papers. So when you click on that, first link you see is for Mr. Davies' interactive PDF of past papers. We're not going there, we're going into the table, and it's the 2024 paper 2. Now when you click on that, that'll open up, and then you can see the section 2 paper, same as the candidates did on the 25th of April 2024. It's 2.5 hours all in. That was for the 25 multiple choice questions, which we've done in another video. And then there is this part, the 110 marks written paper. We're doing this over 3 videos, so this is part 1. Questions 1 to 6, firstly, that's the dynamics and space stuff. And we start with graphs of motion. As usual, have a go at the questions first, and then come back and you'll see how we have done them. So, question 1. The graph represents the motion of a bus travelling along a straight level road between 2 stops. And we can see how its motion is changing from points A, B, C and D. And in part A of the question, we have to describe the motion of the bus between A and B. Well, it's sloping up the way, it's got a constant positive gradient, and that represents a constant acceleration. And then we also have to describe the motion of the bus between points B and C. So have a look at the graph. It's a horizontal flat line. That means the speed is not changing. So it's got a constant velocity or a constant speed there. Then between C and D, it is slowing down. It's decelerating. The graph's got a negative gradient. And then for part B, we have to calculate that acceleration between C and D. So let me go back up to the graph. I'm going to do this beside the graph so we can see the numbers at the same time as I do the calculation here. So we go to our relationship sheet. We're looking for the acceleration equation, A equals V minus U over T. Final speed at point D is 0. The starting speed was 9 meters per second. And the time it took between C and D, well, point C is at 60 seconds and point D appears to be at 72 seconds. So 72 minus 60 means the time for it to slow down was 12 seconds. And that gives us an answer of negative 0.75 meters per second squared. Now I better write it in the right space. So make the little shopping list. Start speed was 9 meters per second, final speed was 0, and the time for that change was 12 seconds. So if we rewrite that here, 0 minus 9 divided by 12 is minus 0.75 meters per second squared. Oh, wrong unit. Minus 2. In part C, determine the distance travelled by the bus between points A and D. Again, that's the whole journey. So distance gone from a speed time graph means we have to work out the area under the graph. So I'm going to chop it up into little sections that are either triangles or rectangles, and we're going to work out the area of each of those 3 sections. Then we're going to add all 3 of those together, and the area under the graph is equal to the distance gone. So the first area is a triangle. We do a half the base times the height, plus the rectangle, area 2, and then another triangle again, half the base times the height. So for the first area, it will be a half times the base is 20, the height is 9. The orange triangle there's got a base of 40 and the height of 9. And then the last area, area 3, is also a triangle, so if we do a half the base times the height, it's a half times 12 times 9. That gives us 3 areas of 90 plus 360 plus 54, and a total of 504 metres is the distance gone. And again, I better make sure that I write that in the correct space in the paper. This is part C, so fill it all in. There's my 504 metres. Okay, on to question 2. A triathlon is an endurance race consisting of 3 stages: swimming, cycling and running. And the first stage is a 1.5 kilometre open water swim. And at one point during the swim, the unbalanced forward force is 25 newtons on a bearing of 0.90. And at this point, the current exerts a force on the triathlete of 12 newtons at a bearing of 180. And by scale diagram or otherwise, determine the magnitude of the resultant of these forces. In other words, we have to add these two forces together as vectors and state what the result of adding them together is. So we need to do a vector diagram. I always start doing a little crosshair and then draw one of the vectors starting from that crosshair. I'm going to choose the 25 Newton one. And then at the end of the first one, at the nose of the first one, we're going to put the tail of the second vector and then draw the 12 Newton vector straight down the way. And then I can also mark on my start and finish point. And then draw a line from start to finish that represents where did we come from, where did we go. I'm doing it in red there and putting a double arrow to show that that's the result of adding those two forces together as vectors. Now when it says by drawing a scale diagram or otherwise means we're going to use Pythagoras to work out the hypotenuse of that right-angled triangle. So it'll be 25 squared plus 12 squared, all square rooted. And then when you do that, you get a value of r. As the square root of 769 is 28 newtons rounded to two significant figures. And why am I rounding it to two sig figs? Because the other two forces are to two sig figs as well. Then 2 part A, part 1, part B. This is by scale diagram or otherwise determine the direction of the resultant of these forces. So I'm going to resketch my diagram again, and we're interested in that little angle there, angle X, because we want the direction from start to finish. Now, if you measure that from north, it's a right angle between north and east, or between north and the 25 Newton vector. So if we work out X, we're going to add 90 degrees to it to get the bearing from north. So let's work out X first. Now we can work out tan X is the opposite over the adjacent side. Well, the opposite side to X is the 12 Newton, the adjacent is the 25. And if you do that on your calculator, tan X is equal to 0.48. Therefore X, if you press shift tan on your calculator, gives you 26 degrees, again to two sig figs. And if we want that as a bearing from north, we're going to add the 90 degrees to it. And we get 116, no units for bearings, just a 3-figure number. You could also have said 26 degrees south of east, and you would still have got that right. And then moving on to part 2, it says the triathlete has a mass of 75 kilograms. Calculate the acceleration of the triathlete. Well, there's his mass, and if we want the acceleration, then the other thing we're going to need is the resultant force acting on them. We've already calculated that. That resultant force was 28 newtons. So by using Newton's second law, F equals ma, we can substitute in the values for the force and the mass and then rearrange it. So 28 divided by 75 will give us the acceleration, and that gives us 0.37 metres per second squared. And because this is a vectors question, we should always take care to include the direction of that acceleration as well. And that acceleration is going to be in the same direction as the resultant force was, so a bearing of 116. And bear in mind that if Roman numerals are used in the question numbering, so this is part 2 or part II as some people say, then it means it's connected to the previous part of the question. Roman numerals are used if you're going to need a bit of information from the previous part of the question and carry it forward to the next part. So watch out for Roman numerals. In fact, this is maybe a good time to have a look at the SQA marking instructions, which you will also find on the Calder Glen High School webpage. So if we go to the National 5 Physics page, go to the table of past papers, and the marking instructions are on the right hand side of the table there. So I'm clicking on the 2024 marking instructions and going to question 2, part A, part 2. And there is our answer of 0.37 metres per second squared for the acceleration with the bearing of 116. And notice on the right hand side there, it says direction required for the final mark. So if you don't put the direction in, you're going to lose that final mark there. So in vectors questions, always make sure you include your directions. Okay, moving on, question 2, part B. This is a completely different part of the question, so we don't need any of the previous information. It says the second stage of the triathlon is a 40-kilometre cycle. Suggest one way in which the triathlete could reduce the frictional forces acting against them when cycling. Well, there's a number of things you could write here. You could say that you could cycle in a tucked position, or wear some streamlined clothing, wear some lycra or tight clothing. Anything there that would reduce the friction acting on them. In question 2, part C, the third stage of the triathlon involves running 4 laps of a 2.5 kilometre course, and the triathlete takes 38 minutes to complete the stage, and we've to determine the average speed of the triathlete for this stage. Well, when you see the word determine, that means it's a straightforward calculation, but there's an extra little bit to do as well. And in this case, we're going to work out average speed equals distance over time. And the little extra bit here is that it's 4 laps of a 2.5 kilometre course. So the distance is going to be 10,000 metres. 4 times 2.5 kilometres is 10 kilometres. And we're told the time is 38 minutes. So again, you're having to convert that into seconds. So average speed is distance over time, and that'll be 10,000 divided by 38 times 60. And that gives us our average speed of 4.4 metres per second. So watch out in determine questions that there's always a little bit extra you need to do when you're substituting your numbers in. And then question 2, part C, part 2, state the magnitude of the average velocity of the triathlete for this stage. Well, velocity is a vector, so you only have to think about where did you start and where did you finish? Where did you come from? Where did you go? Well, they start and finish at the same point, so that means that their average velocity will be 0 because their displacement will be 0. So 0 metres per second there. And that was the vectors question. Pretty tricky. A lot of marks there on vectors. Anyway, moving on. Question 3, we're on to forces. A board slide is a common trick where a skateboarder uses the middle of the skateboard to slide along a horizontal rail. And the skateboarder and his board have got a mass of 65 kilograms. At the start of the rail, he's moving at 7 metres per second, and at the end of the rail, he's only moving at 3 metres per second. And we've to determine the decrease in kinetic energy as the skateboarder and his board slide along the length of the rail. 4 marks here. So it's all about the kinetic energy at the start, which we can work out by doing a half his mass times his initial speed squared, which was 7. And if you do that in your calculator, you'll get 1592.5 joules. And don't round it at this stage. Don't round it till the very end. His kinetic energy at the end of the rail is a half his mass times his final velocity squared. So half times 65 times 3 squared gives you 292.5 joules. And then the difference between the two of them will be the change in his kinetic energy. So if we subtract the final from the initial one, it will give us the decrease in kinetic energy of 1,300 joules. So don't round anything at the halfway stage, only round your answer at the very end. 3A part 2, the length of the rail is 2 metres. Calculate the average frictional force between the rail and the skateboard. Well, it's friction that's doing the work to slow the skateboard down. So we're looking for the work done relationship here. Work done equals force times distance. And remember those Roman numerals? This is part 2 of the question. So we're going to need the decrease in kinetic energy from part 1. And that was equal to 1,300 joules. And it's that loss in kinetic energy that's changed into heat due to friction to slow the skateboarder down. So we're subbing in the 1,300 for the work done. The distance was 2 metres, and then we rearrange that to get the frictional force will be 1,300 divided by 2 is 650 newtons. That's pretty tricky. But again, remember, Roman numerals means the two parts of the question are connected. In part B, the skateboarder and the board slide off the end of the rail, and we have to sketch the path of the skateboarder between leaving the rail and reaching the ground. So a smooth curve showing that downwards projectile path for 1 mark. Okay, moving on, question 4, and we're on to the space questions. So NASA is planning a crewed mission to the moon, and part of the mission includes placing a spacecraft in orbit at an altitude of 140 kilometres above the surface of the moon. And the graph shows the gravitational field strength at different altitudes above the surface of the moon. So straight away we can work out what G will be at a height of 140 kilometres above the moon. If we just read that off, it's about 1.4 newtons per kilogram, and we're probably going to need that. It says one of the astronauts selected for the mission has a mass of 67 kilograms. Calculate the weight of this astronaut when they are at an altitude of 140 kilometres above the surface of the moon. Well, we're using W equals mg here. The mass was 67. The value of G at that height is 1.4. Just checking that by putting a couple of lines on. So G is equal to 1.4 and gives us the weight of the astronaut at that height is 94 newtons. Again, rounding that to two significant figures, same as the numbers in the question. For part B, once the spacecraft is in orbit, some of the astronauts will travel to the surface of the moon in a transportation module, and they remain on the moon for about a week. Describe one physics-related challenge these astronauts will face while they're on the surface of the moon. Well, there's lots you could write here, but I'm going for the fact that there's no atmosphere on the moon and therefore they would have to wear pressurised spacesuits. Or alternatively, you could have mentioned that there's extreme temperatures during the day and the night that the astronauts' spacesuits would have to deal with. Just 1 mark there, so either of those. And in part C, after spending time on the moon, the astronauts return to the orbiting spacecraft using the transportation module. And during the first part of the return journey, the rockets on the transportation module exert a constant upwards force, and we have to state what would happen to the acceleration during this part of the journey. And then it says, you must justify your answer. Well, I think a little diagram would come in handy here so we can see the thing lifting off from the moon. So I've labelled it with the weight downwards and the thrust upwards. And we're told that that thrust is a constant upwards force. So as the craft rises, it's going to use fuel, so its weight is going to decrease. G will also decrease, and therefore the unbalanced force upwards will increase, and that means that the acceleration upwards will increase. That was a 3-mark question, quite a lot you had to write there. So let's have another look at the marking instructions, see what those 3 marks were for. So first mark for saying that the acceleration increases. Second mark was for saying that that was because the mass goes down as the fuel is used up. And the final mark is for saying that the weight decreases or the unbalanced force increases. And also notice on the right hand side there it says this is a must justify question. And what that means is you can't just have a guess here and either say the acceleration increases or decreases. Even if you guess correctly and you say the acceleration increases, you will not get any marks unless you justify your answer with some correct physics there. That's pretty tricky. Watch out for these must justify questions. Right, question 5. Question 5 is the first of the use your knowledge of physics questions. These are open-ended questions. Most people leave these until the very end when they've got a bit of time at the end of the paper. But let's have a go at this one just now. It's a space question. It says around 500 years ago, Nicholas Copernicus, a Polish astronomer, proposed a model of the universe with the sun motionless at the centre and the stars fixed in position in the night sky. Using your knowledge of physics, comment on this model. Now, there's no black and white, hard and fast answer to these questions. This is just about you displaying your knowledge of physics and being able to construct a good answer here. It's 3 marks for a good answer, 2 if it's reasonable, 1 if it's pretty limited, and 0 marks if there's no knowledge of physics displayed. And bear in mind, this is my answer. There's no such thing as a right answer, and I don't know if this would get me 3 out of 3. But here we go. So, previous ideas to this stated that the Earth was at the centre and everything moved around the Earth. And this was the early idea adopted by the Greeks, one of whom was Aristotle. Now, this early idea seemed intuitively correct as we see the sun and the stars moving across the sky and we don't feel the Earth rotating. And we also don't sense that the Earth is orbiting around the sun. But when we look at the planets appear to wander across the sky, which couldn't be explained using an Earth-centred model. But a sun-centred model, also called a heliocentric model, that can explain the motion of the planets. And we now also know that the stars are not at fixed positions, they're not at fixed distances from the Earth. And in fact, we now know that distant galaxies are moving away from us at an accelerating rate due to dark energy, and we can measure this expansion using the redshift of the light from those distant galaxies. Now, would that get me 3 marks? I don't know, and if I've got time at the end of the exam, I'm going to come back to this question and see if I can write down anything more. Anyway, moving on. Question 6, still on space. Launched in 2022, the James Webb Space Telescope is the world's premier space-based science observatory. There's a lot of reading in these questions. Sometimes the trick is just to go to the question and see what you're asked. So part A says, state an advantage of using a space-based telescope compared to a ground-based telescope. Well, there'll be no atmospheric pollution or interference from anything on the ground, no light pollution. Then part B, in 2023, the James Webb Space Telescope was used to study the exoplanet LHS 475b. A strange naming system for these things, but hey-ho, state what's meant by the term exoplanet. Well, that's a planet that's outside of our solar system, or a planet that is orbiting another star. And for part 2, LHS 475b is orbiting a star in the constellation Octans, and the star's 41 light years away, and we've to determine the distance in metres from this star to the Earth. We're going to use distance equals speed times time. Speed of light is 3 times 10 to the 8 metres per second, and then we need the time in 41 years. So it's going to be 41 times 365.25 days. 24 hours in a day, so we multiply by 24 and then multiply by 60 minutes times 60 seconds. And that whole bracketed term there is the number of seconds in 41 years. And so light will have travelled 3.9 times 10 to the 17 metres in that 41 years. It's a huge distance. So remember, a light year is not a time, it's a distance in space that you can work out from distance equals speed times time. Then 6 part C, the line spectrum from a star is shown along with the line spectra of the elements hydrogen, helium, mercury and nitrogen. And we've to determine which of the elements are present in the star. So really all we're doing here is picking out which of the elements' barcodes are present in the star spectrum. So the line in the nitrogen one is in the star, and if we work our way along the nitrogen one, then that whole pattern appears in the star spectrum. So nitrogen's present, and so is, let's try a helium as well. That line is in the star spectrum, so is that one there, and if we work our way along, all of them are present in the star spectrum. But if we look at hydrogen and mercury, then they are not present in the star's spectrum. So if the lines are missing in the star spectrum, then those elements aren't present. So it's only nitrogen and helium. 1 mark for both of them. And that is it for the dynamics and space questions. Question 7's on electricity, and we will come back to that in part 2 of the video. Oh no, wait a minute, I said I would go back and have another look at my open-ended question. If ever you've got a couple of minutes left at the end then always try and add something else in. Remember, this question was about the model of the solar system, so I'm going to draw a little solar system. Don't know if this will get me any marks or not, but I know the order of the planets in the solar system. The Sun is at the centre. We've got our asteroid belt there as well. We are here, and the Earth takes 365.25 days to orbit the Sun. It rotates once on its own axis every 24 hours. Our solar system's part of the Milky Way galaxy, and the universe is 13.8 billion years old. Will that get me any more marks? I don't know, but it would certainly increase my chances. Anyway, that's it for part 1 of the 2024 written paper. We'll see you in the next one.